I hope you're all doing okay. Today we get to talk about economic growth. First of all, I love the Hans Rosling video, and I hope you've watched that before we start here today. And indeed, the very next slide is a clicker question about that Hans Rosling video. Which of the following is not true according to the Hans Rosling video? A, by modern standards, 200 years ago, every country in the world was poor and sick. B, in its impact on health, the Spanish flu epidemic was a bigger disaster than the Great Depression. C, even today, Shanghai is much poorer and sicker than Italy. D, life expectancy in the poorest countries today is better than life expectancy in the richest countries 200 years ago. E, low GDP per capita doesn't lead to life expectancy as low as it used to. Okay, so answer. Okay, so now let me go back through these. So first of all, most of these are true. By modern standards, 200 years ago, every country in the world indeed was poor and sick. The Spanish flu epidemic was a very big deal. Life expectancy is better in the poorest countries today than in the richest countries 200 years ago. And at low levels of income, life expectancy is better than it used to be. But Shanghai is really about the same as Italy now. So let's now turn to chapter 8 and some of the other things we'll talk about. In chapter 8, you learn about the closed economy Solow model, how a country's standard of living depends on its saving and population growth rates, how to use the golden rule to find the optimal saving rate and capital stock. One thing you can see here is that this is really about saving and capital accumulation. So there are a lot of things I talked about in the previous lecture that can go wrong to block economic growth. And this chapter is really focused in on what if you don't save enough, what if you don't build enough factories and make enough machines. But before we get into that, let's talk a little bit about why growth matters. It isn't just about GDP narrowly. In the infant mortality is about 20%. That is, about 20% of babies die in the first year in the poorest fifth of all countries. But in the richest fifth of countries, it's only 0.4%. In Pakistan, 85% of people live on less than $2 a day. So you might think money isn't everything, but that's not easy to have a life with living on less than $2 a day. 1/4 of the poorest countries have had famines during the past 3 decades. Poverty is associated with oppression of women and minorities. So there are a lot of good things that come from economic growth. It raises living standards and reduces poverty. Now, let's think about growth per se. Even small rates of growth can make a big difference. And the rule of 70 that we've talked about before in the class is helpful for thinking about this. Growth in per capita GDP of 1% per year doubles per capita GDP in 70 years, because in 70 years times 1% per year, you got a 70% platonic increase, which is a doubling. Growth of 2% per year doubles per capita GDP in 35 years. Growth in per capita GDP of 3.5% per year doubles per capita GDP in 20 years. And if you can grow 7% per year, as China did for quite a while, you can double per capita GDP in 10 years. So growth rates that can seem modest can really transform things over time. if the annual growth rate of US real per capita GDP had been just 0.1% higher for 10 years, the average person would have earned $2,782 more during the decade. Okay, so growth theory can make a big difference to the extent that we actually do understand economic growth, and there are real limitations to how well economists do understand economic growth. But we want to ask questions like why poor countries are poor, design policies that can help them grow, and learn how our own growth rate is affected by shocks and our government's policies. Now, I love these pictures that show some of the difference in standards of living. First, we've got a family in the United Kingdom, which is a fairly rich country, and they've got all their stuff there displayed. Here's, by contrast, oh, so that's what you get at 36,000 a year, which is, you know, hopefully many of you will end up with a higher per capita income, but that's not necessarily, that's not too shabby in a worldwide context. They've also got a life expectancy of 80 years and a lot of literacy. Now let's compare to Mexico. So here's a family with all its possessions in Mexico, a middle-income country. GDP per capita, 14,270, life expectancy, 76 years, adult literacy, 86%. Finally, here's a typical family with all their possessions in Mali, which is a poor country. So you can see the dramatic difference there. This is a per capita GDP of $1,090 and life expectancy 52 years and adult literacy of 46%. So you can see there's a big difference between being in a poor country, you know, growing up in a poor country and growing up in a rich country. Okay, so the Solow model is really going to focus on capital accumulation. It's due to Robert Solow, who won the Nobel Prize for contributions to the study of economic growth. It's, this is, you know, an important paradigm and something that economists know. Okay. Now, how is the Solow model different from Chapter 3's model? The big difference is that we're bringing in dynamics. Capital is no longer fixed. Investment causes it to grow. Depreciation causes it to shrink. And so this may well be the first time you've seen a truly dynamic model in action. Also, the amount of labor is no longer fixed. Population growth causes it to grow. Now, we've got a bigger change in how we're treating the amount of capital because we're making it endogenous, determined by the model itself. Here, to the extent we have population growth making labor grow, it's basically just exogenous. We're complicating things in some ways, and to make the model manageable, we'll simplify in some others. We're going to make the consumption function simpler. We're going to leave out government purchases and taxes. That's only to simplify the presentation. We'll represent fiscal policy experiments by changes in the national saving rate. And there's some other small differences. Okay, so let's review the production function. In aggregate terms, GDP is a function of the amount of capital and labor, and of course, hiding behind the scenes is the level of technology, which we'll make explicit later, but not yet. Now, we want to do things on a per worker basis. It's similar in spirit to doing things on a per capita basis, but it's a little cleaner to do it on a per worker basis. So define little y as the total GDP, big Y, divided by the amount of the number of workers, that's output per worker, Y over L. Little k, again, the little k is capital per worker, where the big K was total capital. Now, if we assume constant returns to scale, as we're going to do, then if you multiply the inputs each by Z, twice the capital, twice the labor, you get twice the output. But this makes it easy to transform into terms of the little letters, because we can pick, instead of doubling, suppose we multiply by 1 over capital L. Then we find that Y over L is a function of K over L and L over L, but L over L is just 1. So we get output per worker is a function of capital per worker and 1, but 1 isn't going anywhere. So we'll use the little f to leave out the 1 that isn't going anywhere. Output per worker, little y, is equal to function little f of capital per worker. Here's a picture of it. You have decreasing returns in capital alone. Think of this as what's going on for one worker. Since it's one worker, you're not increasing the amount of labor. So even though there's constant returns in capital and labor combined, there's decreasing returns in capital alone. And remember, the replication argument only applied to when you doubled everything. Here we're not. We're increasing the amount of capital while leaving the number of workers as just 1. Okay, so there, that slope is the marginal product of capital, little f of k plus 1 minus little f of k. And that marginal product of capital declines as you go to higher levels of capital. Okay, now remember, we've left government purchases in the background, so we can say GDP is consumption plus investment. Note we're also dealing with a closed economy. We'll come back to the open economy after we do chapters 8 and 9. In per worker terms, just by dividing everything in both sides of the equation by capital L, I find that output per worker is equal to consumption per worker plus investment per worker. Now, I'm going to have a very simple consumption function. I've got a little s, which is the saving rate, the fraction of income that's saved. Little s is an exogenous parameter. It's the only lowercase variable that's not equal to its uppercase version divided by L. And the consumption function is just, if S is the saving rate, 1 minus S is the consuming rate, whatever you're not saving. So you just take the 1 minus S, how much you don't save, times GDP per person, output per person, and then you get consumption per worker. Sorry, I said per person, but 1 minus S times output per worker is equal to consumption per worker. And saving, the total saving is equal to the saving rate times output per worker. That's the saving per worker. And you can see how the algebra goes, but it would be surprising if the saving weren't the saving rate times the output per worker. The national income identity is output per worker equals consumption per worker plus investment per worker. If we rearrange that, we find that investment is equal to output per worker minus consumption per worker. That is equal to the saving rate times output per worker. And so investment equals saving. So this is a long run model here, like in chapter 3. In fact, you can think of the Solow growth model as talking about the long run and the very long run. It's all happening after prices have adjusted, but we get to talk about before and after capital has adjusted to where it'll eventually be due to the investment and depreciation. So now let's make another interesting move. In the investment per worker is equal to the saving rate times output per worker, but we also know that output per worker is little f of capital per worker. Okay, so we can draw a picture of that. There's little f of capital per worker.
You'll need to unlock your iPhone first.
And now if we take the saving rate times f of k, we get the blue curve, which is down lower. Okay, so that's the total amount of investment, little s times f of k, f of little k. Now, imagine you have a particular starting level of capital K1. Now you can see the level of output, and you can see the level output per worker. Sorry, yeah, you've got the initial level of capital per worker. Then you can see the initial level of output per worker and the initial level of investment per worker. And consumption per worker, you can see in that gap between output per worker and investment per worker. So consumption is what's left over of output after you invest some of it. Now we need to bring in depreciation. Little delta is the rate of depreciation, which means the fraction of the capital stock that wears out each period. Now, delta is just a constant, and so if you look at depreciation per worker, that's just a straight line out of the origin as a function of capital per worker. Slope of that line is always delta. One more unit of capital, you're going to get delta more units of depreciation. Okay, so we can now look at capital accumulation. And the basic idea is that investment increases the capital stock, depreciation reduces it. So the change in the capital stock is investment minus depreciation. Now in the book, Mankey sometimes uses delta for this, and I may have that in some slides, but you've pretty much all had a bit of calculus, at least, so that some of you a lot of calculus, so we can write it as dkdt, the rate of change of capital per worker over time. The rate of change in the capital per worker is equal to investment per worker minus the depreciation rate times the capital stock, which is depreciation per worker. So dkdt equals I minus delta k. Now, if we plug in that investment is equal to the saving rate times f of k, this becomes the equation dkdt, the rate of change of the capital stock, is equal to sf of k minus delta k. And this we can graph. So, you know, that is a very important equation. It's the central equation of the Solow model, determining the behavior of capital over time, which in turn determines the behavior of everything else because all the other endogenous variables depend on k. For example, income per person is f of k, consumption per person is 1 minus s times f of k. You know, everything is driven, everything is hanging on the capital stock or the capital per worker. Now, let's first talk about the steady state. If the rate of change of the capital stock is sf of k minus delta k, if that's equal to 0, you have a steady state, meaning the capital per worker isn't changing. So what would it take for that? Investment would have to be just enough to cover depreciation. Sf of k equals delta k. Then capital per worker will stay constant, that is dkdt equals 0. This occurs at only one value of k, which we're going to call k star, or this, which is the notation for the steady state capital stock. Let's draw a picture of this. There's sf of k. There's delta k. So we've got the curved line gives you investment per worker. The straight line gives you depreciation per worker, where investment per worker equals depreciation per worker. You have the steady state capital stock. So K star is the level of capital at which you have the intersection between those two curves, one of which is a straight line. Okay, now what's going to happen if we're away from the steady state? I've brought back the dk dt equals sf of k minus delta k equation to help us out. Suppose the initial capital stock K1 is below that level. Then if you look closely, you can see that investment is above depreciation. So you're making more new capital than what's wearing out. There's investment, there's depreciation. The gap is going to be dk dt. And as I warned you, we'll sometimes have the man cube notation of delta k when it's really dk dt. So capital stock is increasing. You go from K1 to K2, but at K2, same thing happens. Investment is greater than depreciation. So you've got dk dt positive, and so capital increases. Where does this stop? Well, as long as little k is less than little k star, investment will exceed depreciation, and little k will continue to grow towards k star. So okay, so let's do a clicker question here. Suppose instead of K1 being at a lower level of capital per worker, suppose it's at a higher level of capital. What is going to happen? Are we going to have dk dt equal to 0? Are we going to have dk dt greater than 0 and move towards the steady state? Are we going to have dk dt less than 0 and move towards the steady state? Are we going to have dk dt greater than 0 and move away from the steady state? Or are we going to have dk dt less than 0 and move away from the steady state? So stop your video and answer the question. Okay, so what's going to happen? Well, over here, we have depreciation greater than investment. So the wearing out of capital is greater than the new capital that's built. Therefore, depreciation is the dominant force. The capital stock will be going down. So dk dt will be less than 0. And as you can see, if capital is going down, you're going towards the steady state. So therefore, dk dt is less than 0 towards the steady state. The answer is C. Okay, we've talked about Cobb-Douglas a lot. Overall output is equal to the technology parameter A times capital to the alpha power times labor to the 1 minus alpha power. That's a little Greek letter alpha there. Now, suppose we divide by capital L, then we can do this. We can get y over L on the left, and capital L is equal to L to the alpha times L to the 1 minus alpha. So dividing by the right-hand side by L, I can get, A times K over L to the alpha and L over L to the 1 minus alpha. So at the end of the day, I find that output per worker is equal to the technology parameter times K to the little alpha. And if any of this algebra seems a little dicey to you, stop and work it out till you've got it clear. And definitely remember, you can talk to me in office hours. It's really easy to set up a time and meet for a video chat. Just shoot me an email suggesting a time. All right. So anyway, output per worker with Cobb-Douglas is going to be equal to the technology parameter A times capital per worker to the alpha power. Just opening my key line there. Okay, so let's let's put this into logarithmic form. We've got the natural logarithm. We've got log output per worker is equal to log A plus alpha log K. So you notice this is looking like a pretty simple equation. Once we take logs, we have log output per worker linear in log capital per worker. Okay, now if we use logarithms, it becomes relatively easy to find the equations for the steady state capital stock. So let's go through that. So we have this equation, saving rate times steady state output is equal to depreciation rate times steady state capital. Okay, now if I plug in the Cobb-Douglas equation for steady state output, I get saving rate times technology parameter A times K star to the alpha equals delta K star. This is going to simplify a lot when we take logarithms. So log saving rate plus log A plus alpha log K star. So notice how similar that is to, we've got what we had on the previous slide as part of the things, but now we've got the saving rate in there too. Log S plus log A plus alpha log K star equals log delta plus log K star. It simplifies beautifully with the logarithms. So let me now transform the equation a little bit or rearrange it. What I want to do is I want to get all the terms involving log steady state capital on the right-hand side. If I do that, I can do that just by subtracting alpha log K star. So then I get log S plus log A minus log delta. So I subtracted log delta from both sides equals 1 minus alpha log K star. Then I can solve for log K star just by dividing by 1 minus alpha. And I find the following. Log K star is the quantity 1 over 1 minus alpha. Or maybe I should say the quantity 1 over the quantity 1 minus alpha times log S plus log A minus log delta. So one thing you can notice here is higher saving rate raises the steady state capital stock. Better technology raises the steady state capital stock, but the higher depreciation rate lowers the steady state capital stock. Okay. Okay, so here's just a repeat of what we had before, but now let's plug in a particular realistic value of alpha equals a third. So if alpha equals a third, then 1 over the quantity 1 minus alpha is 1.5. Why is that? Well, 1 minus alpha is 2/3, and 1 over 2/3 is equal to 1.5. Also, if alpha is equal to a third, then alpha over 1 minus alpha is a half, because then you get a third over 2/3, and a third over 2/3 is a half. We're going to need that on the next slide. Because what I want to do now is to find steady state output as well. So we know that log of K star is 1 over 1 minus alpha, which in this case is 1.5 times the quantity log S plus log A minus log delta. And I'm not speaking every last parenthesis, but you can see it in front of you. Let's now plug in log of steady state output. Log of Y star equals log A plus alpha log K star. Just substituting in, I get this. But now I want to combine the two terms involving log A. Okay. And if I combine the two terms involving log A, I get quantity 1 over the quantity 1 minus alpha times log A. So how do I get that? Well, I'm adding 1 plus alpha over 1 minus alpha. And if you do the math there, 1 plus alpha over 1 minus alpha is going to equal 1 over 1 minus alpha. But the alpha over 1 minus alpha continues there as the coefficient of log S minus log delta. Okay, and there down at the bottom, I've laid out the algebra for 1 plus alpha over 1 minus alpha being 1 over 1 minus alpha. So what happens, I take the one and make it 1 minus alpha over 1 minus alpha. So I've got the same denominator in both cases, but in the numerator, 1 minus alpha plus alpha equals 1. Okay, so that's how I got that. So if alpha is a third, what are you going to get? So this is a clicker question. What is the elasticity of steady state output with respect to technology A? If you've got everything in logs, the elasticity is just the coefficient. So we're really just asking what the coefficient, given that we have log of steady state output on the left, we're really just asking what the coefficient of what the coefficient of log A is going to be. Is it closer to 0, a half, 1, 1.5, or 2? So stop the video and answer that. Okay, what are we going to get? Well, the coefficient of log A is the elasticity, because we've got logs on both sides. We've got log output depending on log technology, or log steady state output depending on log technology. So the coefficient we're concerned with is 1 over the quantity 1 minus alpha. Well, 1 minus alpha is 2/3. 1 over 2/3 is 1.5. So the answer is 1.5. So that's interesting. A 1% improvement in multiplicative technology A is going to get us a 1.5% increase in steady state output. And the reason is it has not only a direct effect, but it also increases the capital stock. Okay, now let's do another clicker question. Same alpha equals a third assumption. What's the elasticity of steady state output with respect to the saving rate, S? Okay, now you're going to look for a different coefficient, which is still in logs. So the coefficients are elasticities. What is it? Is it closest to 0, a half, 1, 1.5, 2? Stop the video and answer. Okay, well, what do we get? Well, the coefficient of log S is alpha over 1 minus alpha. That's a third over 2/3, which is a half. So the answer is B. Imagine that new technology that doesn't affect the technology. Imagine a change in technology that doesn't affect the technology parameter A, but does change delta, because there is a sense in which delta is itself a technology parameter, though usually when we say technology parameter, I'm going to mean A. But suppose delta does change, and it would be an improvement in technology if things wore out less fast. But suppose alpha is a third. What's the elasticity of steady state output with respect to the depreciation rate, delta? Okay, and now I'm going to represent this as a negative, because we know higher depreciation is going to be, bad for steady state output, Y star. What is it going to be? Stop the video and answer. Okay, so we had a coefficient of minus alpha over 1 minus alpha. I can go back to the previous slide here very briefly. You can see I've got the minus sign on log delta, so I get minus alpha over 1 minus alpha. Okay, but alpha is a third, so that's minus a third over 2/3, which is minus a half. So the answer is B. Okay, now here we have something actually quite difficult. What is, we're talking about a change in the logarithm. So we're talking about a percent change in something that already looks like an annual percent change. And so there's something that's just unavoidably difficult, and we can't escape it. The thing that's unavoidably difficult is if I go down from 0.05 per year to 0.049 per year, that is a 2% change in the sense that the logarithm goes down by 0.02. How do we think about this? Well, what you really want to do when thinking about the logarithm is think about the logarithm of the ratio. So 0.049 divided by 0.05 is equal to 0.98, and the logarithm of 0.98 is that's basically 2% below 1. So the logarithm of 0.08 is minus 0.02. So it's just unavoidably difficult. You have to ignore here the fact that they're already measured in percent. We're not talking about percentage points. Like a 1 percentage point decrease in 5% per year would take it down to 4% per year. But if you went from 5% per year down to 4% per year, that would be a 1 percentage point decrease, but it would be a 20% decrease because it's like going from 5 to 4 of anything is like a 20% decrease approximately. So anyway, the cleanest way to deal with it is to actually just divide. You divide 0.049 by 0.05 and then say that's 0.98. How big a percent decrease is that from 1? So this is actually a 2% decrease. So we know we have an elasticity of minus 0.5. If you multiply an elasticity of minus 0.5 times a change of minus 2%, what is the percentage change on steady state output? 0, closest to 0, 0.5%, 1%, 1.5%, 2%. Stop the video and answer. Okay, so here's the answer where we have a 2% decrease, so we have minus 2% times minus a half elasticity, and so minus a half times minus 2% is plus 1%. So this 2% decrease in the depreciation rate raises steady state output by 1%. And again, you just have to be very clear, and that decrease from 5% per year to 4.9% per year is a 2% decrease. Yes, it's I guess it's a 1/10 of 1 percentage point, but that's not relevant. It's the fact that it's a 2% decrease. As you can, and again, the safest way to deal with that is to divide the 0.049 by the 0.05. This is unavoidably difficult, and there is an exercise on the course website that'll help you get practice with this. Okay, now, so far we've been measuring technology by the parameter A. It's often called the multiplicative technology parameter. But there is another way that's sometimes convenient. Suppose we define E so that E to the 1 minus alpha equals A. Okay, what happens if I plug that in? Where I have A, I plug in e to the 1 minus alpha. So y was equal to a, k to the alpha, L to the 1 minus alpha. That's totally equivalent to saying y equals e to the 1 minus alpha times k to the alpha times L to the 1 minus alpha. And now I can combine the e with the L and get output is equal to k to the alpha times EL to the 1 minus alpha. What's the advantage here? Now I can think of this as the effective amount of labor, and E is kind of being, the efficiency of labor. So it's measuring technology in a way so that if E is 2, that means that one worker can do the work that, when E was equal to 1, it took 2 workers to do. So one person is like the power of 2, or is like one worker is now like 2 workers in what she can do. E is called labor augmenting technology. So A is multiplicative technology, E is labor augmenting technology. And there's a very simple relationship between their percentage changes. The percent change in A is equal to labor share 1 minus alpha times the percent change in E, and that's pretty intuitive. Alpha is capital share, 1 minus alpha is labor share. If you have something that's equivalent, that's as if you were increasing the amount of labor by 1%, you've got to multiply it by labor share because labor is only doing part of the work in making things. Capital is doing the other part of the work. Okay. Okay, now there's a lot here, and let me suggest you know, as you go through this video, you might want to take a break at some point and then come back and watch the rest. I'm going to keep going, but remember that it's very easy for you to stop whenever you want to and take a break. Okay, so now I want to look at our equations if we use the E notation instead of the A notation. They're equivalent here with Cobb-Douglas, they're equivalent, but they do end up looking slightly different. Okay, so just bringing back an equation from before, the log of the steady state capital is equal to 1/1 minus alpha times log S plus log A minus log delta. And I'll let you look at the slides, look at the picture for where the parentheses are. Now let me just substitute in 1 over, if log A equals 1 minus alpha log E, okay, that was on the previous slide, right? Oh, I actually didn't ever take logs, but look at that equation, A equals E to the 1 minus alpha. Take logs of that, I get log A equals 1 minus alpha log E. Okay, just plug that in. I've got where I have A, I have 1 minus alpha log E, but that multiplying by 1 minus alpha just cancels out the dividing by 1 minus alpha that I have out front. So I get log E in front. And this shows you another reason why the talking about things in terms of labor augmenting technology is convenient, because now the steady state capital stock is goes up 1 for 1 with labor augmenting technology. And then the rest of the stuff involving the saving rate and depreciation is really unchanged from before. Now let's look at log steady state output. And again, we have this 1/1 minus alpha times log A, which becomes just log E. And the rest remains the same as before. It's multiplied by alpha over 1 minus alpha because it's output, whereas with the capital stock, it was just 1/1 minus alpha. But in both cases, I got log E. So both steady state output and steady state capital stock go up 1 for 1 with labor augmenting technology. So that's very, very convenient. And it's it can be viewed as the mathematical secret behind some of the tricks that are done in chapter 9. So I don't want to get ahead of myself and talk too much about that, but this is why thinking about things in terms of labor augmenting technology works so well. Okay, now we get to do some comparative statics, or you could even call it comparative dynamics in this case. Let's see what happens. Let's look at an increase in the saving rate. So imagine we're at a steady state, K1 star, so the first steady state that corresponds to saving rate S1. So, but now after I increase the saving rate to S2, I've got a higher curve for investment per worker as a function of capital per worker that raises the new steady state that you're going to grow towards gradually. Because if you look closely, you can see that investment was above depreciation because we didn't do anything to depreciation. That function, that line stays the same, but now we've got extra investment. With depreciation the same, we're going to get more capital, but of course, as we get more capital, that depreciates too, and so there is a limit to what happens. One of the key things about this Solow model that you want to pay attention to is even if you permanently raise the saving rate, you don't have permanently higher growth. You do have a permanently higher capital stock, which gets you permanently higher output, but you'll grow for a while as the capital stock goes to its new higher steady state value, and then things will come to rest again. By the way, I'm able, on my blog, I'm able to make good use of this Solow growth model analogy to talk about weight loss and weight gain. It's very much like this. You have to have a permanent change in behavior to have a permanent loss of weight. And sometimes people think, oh, they can just change their behavior for a little while, lose some weight, and then go back to eating the way they were, and then end up with permanently at that lower weight. I'm sorry, it's much more like this Solow growth model. You need a permanent change in behavior to get a permanent change in weight. If you then, like here, if you made the saving rate go back to what it was, you'd wind up back at the old capital stock. And if you talk about weight loss and weight gain, if you go back to your old behavior, you're going to wind up back at your old weight. You need a permanent change in the saving rate to have a permanent change in the capital stock, permanent change in your behavior to have a permanent change in weight. Many people don't understand that in relation to weight loss, but this Solow growth model is actually very, very helpful in understanding that. And hopefully, what I said about weight loss and weight gain is at least slightly helpful in understanding the Solow growth model too. Okay, so what's the prediction here? The Solow model predicts that countries with higher rates of saving and investment will have higher levels of capital and income per worker in the long run. Are the data consistent with this prediction? So let's look at the graph. So on the horizontal axis, I've got investment as a percentage of output. Okay, that's the little I. And on the vertical axis, I've got Y, basically little y star, income per person, although it's, oh, I'm sorry, this is not, on the horizontal axis, this is not little I. This is little I over little y, basically. But what you do see, or rather little s, sorry, I've got a little s, investment as a percentage of output on the horizontal axis. And on the vertical axis, I've got income per person, which isn't quite the same as income per worker, but it's pretty close. It's the same idea. As long as the number of workers as a fraction of the population isn't different too much, that's going to track along with income per worker. And you can see that higher saving rate does indeed lead to higher income per person. person. Okay, now let's talk about what we would like the steady state capital to be. So, golden rule, the introduction to it. The golden rule is a rule about what you'd want the saving rate to be, given where you'd want the steady state capital to be. So different values of the saving rate lead to different steady states. How do we know which is the best steady state? Well, there are different notions of best, but there's a very simple one that's a great place to start. Let's think of the steady state that has the highest possible consumption per person. Now, in doing this, we're really focused on the very long run. So we're being very patient. We're caring a lot about future generations. But this can be a reasonable thing to do. So we focus on steady state consumption per person, which is 1 minus S times F of K star. An increase in the saving rate leads to higher capital stock and higher output, higher capital per worker and higher output per worker, which raises C star, but a higher S reduces 1 minus S, which lowers C star. So they're two opposite direction effects. Which one wins out? Let's take a look. We can draw a picture. So let's use this notation. K star gold is the golden rule level of capital, the steady state value of little k that maximizes consumption. I said capital, but I really meant capital per worker. So let's express consumption per worker in terms at the steady state in terms of capital per worker at the steady state. That's equal to output per worker at the steady state minus investment per worker at the steady state, because it's only what's not invested that's left over for consumption. Now we plug in that output per worker is F of K star, and investment in steady state just barely matches depreciation. So we subtract delta K star, right? Because steady state means dk dt equals 0, so investment must equal depreciation, which is depreciation rate times capital, and all of this is done on a per worker basis. Now let's draw a picture of this. So what we do is we graph F of K star, okay, and delta K star. Now we're doing something different here. Before we had SF of K star and equals delta K star to find the steady state. But now what we're doing is we're trying to see how much consumption there is. Consumption is F of K star minus delta K star. So what we want is to have that vertical gap between the curved F of K star and the straight delta K star be as much as possible. Okay, because we can see now what I star gold is there. It's equal to delta K star gold. And we can see what Y star gold is. That's F of K star gold. And the gap between them is C star gold. Okay, so notice we're for the moment disregarding the S times F of K star curve. We'll bring it back when we want to think about what S will get us to here. But at the moment, we're thinking, okay, there's likely to be some saving rate that gets us to any particular steady state capital stock. We want that vertical gap, C star gold, to be as big as possible. How do you get there? Well, if you look really closely, we'll see this in the slides and more explicitly in a minute. But if you look at this picture, you see here the gap is widening because the slope of F of K star, that is F prime of K star, is higher than the slope of this, which is delta, the slope of the delta K star. But over here, the gap is narrowing as we go up because f prime of k star, that is the slope of f of k star, is lower than delta. Okay, so see, the steady state consumption is biggest where the slope of the production function equals the slope of the depreciation rate. That is, where the marginal product of capital equals delta. F prime of k star is equal to the marginal product of capital. Okay. And we are using the fact that thinking about the marginal product of capital on a per worker basis gets you exactly the same answer as if you were thinking of the marginal product of capital overall. Okay. So we have this very interesting condition, marginal product of capital equals depreciation rate. Now, let's think of the transition to the golden rule steady state. Notice, very importantly, the economy does not have a tendency to move towards the golden rule steady state. The only way you can get it to the golden rule is by policy, by getting the saving rate to the appropriate level. If you don't do anything to try to adjust the saving rate, it would only be by pure luck that you'd ever get to the golden rule steady state. Achieving the golden rule requires that policymakers adjust the saving rate little s. This adjustment leads to a new steady state with higher consumption, if they adjust little s upwards, that is. But what happens to consumption during the transition? Actually, oh, I'm sorry. By definition, the golden rule has a higher consumption than any other value. So you're always, unless you're at the golden rule to begin with, you are going to make consumption go up. But let's see what happens along the way. If we start with too much capital, that is above the steady state level, what's going to happen? Well, then increasing C star requires a fall in the saving rate. In the transition, saving and consumption is higher at every moment in time, right? Because if you just save less at the same level of output, you're going to get higher consumption to begin with. And then, you know, the output will go down some, but we know that you're going to the golden rule, which has a higher level of consumption. So we know your consumption is higher initially just because you're saving less with the same level of output per worker. And we know that your consumption is higher in the long run, in the very long run, because after capital is adjusted, because that's the definition of the golden rule. So if you start with too much capital, it's really, you know, you have, it's really fun. You have higher consumption here, you have higher consumption later. What's not to like? Now, you know, output does come down and, you know, investment drops in right away because of the lower saving rate. And then it's a certain fraction of output. So as output comes down, it comes down even more. But, you know, our objective isn't to have higher GDP. Our objective is to have higher consumption. I mean, what's the point of GDP except to be able to use it? Investment is a means to an end, not an end in itself. And you have to remember that. And so higher consumption at all moments in time, this is great. In fact, this is so great that, you know, steady state capital above the golden rule capital stock is considered by economists to be very stupid. So stupid that that situation is called dynamic inefficiency, and curing dynamic inefficiency is great. If you cure dynamic inefficiency, you get higher consumption at all moments of time. But what if you start with too little capital? Now, as we have to increase the saving rate in order to get to a higher steady state capital stock, right? The steady state capital stock has a positive elasticity with respect to the saving rate. As we saw, if we're going to increase the saving rate, that's got to make an immediate drop in consumption. Okay, now, because of the definition of the golden rule, we know that consumption will end up higher in the end, but that initial higher saving rate cuts into our consumption and is painful. So future generations are benefiting, but there's a sacrifice on the part of people right now. You get an increase in output, you get an increase in investment, and you get an increase in consumption in the very long run after capital adjusts. So again, I'm using long run to mean after prices adjust, and very long run to mean after the capital stock also adjusts. So in the very long run, the consumption is higher, but you got to sacrifice with a higher saving rate, lowering your consumption in the nearer term future. We can call that the ordinary long run, but at any rate, consumption doesn't go up until it's been quite some time. So anyway, and this can be a while, it can be 15 years or 25 years, or it can be quite a lot of time. Okay, so now let's take a look at some other equations. Suppose that we meet the golden rule, of having the saving rate times GDP equaling depreciation times the capital stock. And notice that we could divide both sides by capital L, and that would say S times little y equals delta times little k. But, we can also say S times big Y equals delta times big K. That's, oh, I'm sorry, this is not the golden rule. So little s times big Y is equal to delta K. That says that investment, which is S times big Y, is equal to depreciation, which is delta times big K. And again, if we made it little y and little k, that would also be true. But what we have here is that investment equals depreciation. That just means we're at a steady state. So suppose we're at a steady state, but the delta K is greater than MPK times K. So therefore depreciation is greater than the marginal product of capital. And let me remind you of where that means we are relative to the golden rule. So if depreciation is greater than the MPK, that means we've got an MPK that gives us a kind of flat spot, and that means we're above the golden rule. So here I'm above the golden rule because depreciation is greater than the marginal product of capital, right? If we decide to have more capital, we get this low marginal product and this high depreciation. That's not so great. It'd be better to actually have less capital because we lose only a little marginal product of capital, and we save on a lot of wear and tear on capital by having less capital. And of course, we're still in a no population growth and no technological progress case. Here's our clicker question. The economy is at the golden rule level of capital, is A. B, the economy is above the golden rule level of capital. C, the economy is below the golden rule level of capital. D, more than one of the above is possible. Stop the video and answer the question. Okay, here's the answer. I tried to make it easier by laying things out a little bit. If depreciation is higher than the marginal product of capital, that last unit of capital is really dragging you down. It's the wear and tear is greater than what it's producing. So that's a bad thing. That's too much capital. That means you're above the golden rule level of capital. The answer is B, above in the sense of too much capital. Okay, let's talk a little bit about population growth now. Assume the population and labor force grow at rate little n, which is exogenous. So dl dt divided by L, which is equal to d dt of log L is equal to n. Okay, so again, Mankiw has it as delta L, but think of that as dl dt. 1 over L dl dt is the same as d of log L dt. And if that seems hard at all, lay down the calculus for yourself. Calculate d dt of log L. All right, let's do a simple example. Suppose you have 1,000 people in year 1 and the population is growing at 2% per year. How many will you have a year later? You'll have 1,020. Okay, now, when we have population growth, in many ways, it's as if we replace depreciation rate with depreciation rate plus the population growth rate. And why is that? It's because we have this concept of break-even investment, the amount of investment necessary to keep capital per worker constant. So N is going to be the growth rate of workers as well as of overall population. So the idea is, you need to not only replace depreciation, but be able to hand new tools to the new workers that are there because of population growth. Otherwise, the number of tools per worker is going to fall behind. So you got to replace depreciation and you've got to keep up with population growth. And whatever population growth is and growth per worker, which we're assuming is the same thing, if that's 2%, you're going to need to, have 2% of the amount of capital as extra new investment just to keep up with population growth rate above and beyond depreciation. So break-even investment includes delta K to replace capital as it wears out, and NK to equip new workers with capital. Okay. Otherwise, the existing capital stock will be spread more thinly over a larger population of workers if you didn't have the NK. So now, with population growth, the equation of motion for K looks like this. dk dt equals SF of K minus delta plus N times K. That is the quantity delta plus N times K. Okay, so we've got actual investment, and I'm sorry that bracket is in the wrong spot. Should be a little over to the right. Actual investment SFK and break-even investment delta plus NK. So again, the brackets are not in the right place, but SF of K is actual investment and delta plus NK is break-even investment. Okay, so now let's look at the new revised Solow model diagram. What looks like delta K is really dk dt. And we have our steady state. It's a steady state with population growth is where SF of K equals delta plus N times K. Use the same notation K star for that. It's still called the steady state level of capital per worker. Okay, let's think of different levels of population growth. If we have a higher rate of population growth, then we have a higher delta plus N. We go from delta plus N1 to delta plus N2. It's a little bit as if there were a higher depreciation rate, even though it really isn't. But the break-even line goes up, and that reduces the steady state capital stock, as you can see. And then you would gradually, if somehow your population growth rate increased, you would gradually have the steady state capital per worker go down. Now, it's not that your capital stock is literally shrinking, but it is getting spread more thinly over more workers. Okay. So there's a prediction. The Solow model predicts that countries with higher population growth rates will have lower levels of capital and income per worker in the long run. Let's look at the data. Actually, that prediction worked pretty well. Population growth on the horizontal axis, income per person. And remember that little y star goes up with little k star. So a higher, a lower capital per worker with higher population growth leads to lower output per worker. Okay. What about the golden rule with population growth? Well, now let's think of, it's actually, we're changing the objective a little bit. What we want is to have a high steady state level of consumption per worker. Actually, not, rather than, I mean, you could say there was something not nice enough to future generations here, because after all, they're bigger, and yet you're only focusing on their consumption per worker. But at any rate, this is a convenient and easy criterion to focus on consumption per worker, even though there are more workers in the future who possibly should count more, but we're not counting future generations more. We're kind of counting each generation the same amount, even though future generations are bigger. And we're counting each generation equally, even though future generations are bigger, by focusing in on consumption per worker rather than some total level of consumption. Okay, a lot's the same, but instead of delta, we have delta plus n. Now, consumption per worker in the long run steady state is maximized when the marginal product capital equals not delta, but delta plus n, the depreciation rate plus the population growth rate. Equivalently, the marginal product of capital minus depreciation, the marginal product of capital net of depreciation, should equal the population growth. And that's interesting because the marginal product of capital minus the depreciation rate in some simple models is equal to the real interest rate. Okay, so let's do a bit of a clicker question here. Suppose you're at a steady state, and the level of investment is less than marginal product capital times the capital stock. We have population growth, but no technological progress. Where are we at? At the golden rule, above the golden rule, below the golden rule, more than one of the above is possible. Now, this is actually quite hard. Do your best here. You'll learn more by trying and see what you can do, but this is extremely difficult. If you can get it, that's really impressive. Stop the video and answer. Okay, so let me talk about this. So the thing we know is that steady state means S times Y equals delta times K. But then if SY equals delta K, that must mean that delta K is less than MPK times K. So delta must be less than MPK. If MPK is greater than delta, that means each extra unit of capital is producing more extra stuff than depreciation. That makes it look like a good deal in terms of, getting us higher steady state consumption. If MPK is, oh, I'm sorry, I've messed up. The steady state, my SY is not equal to delta K. It's a steady state with population growth, so SY must equal the quantity delta plus N times K, okay, in order for it to be a steady state. That implies that the quantity delta plus N times K is less than MPK, so therefore delta plus N is less than MPK. That means an extra unit of capital produces more than enough to make up for depreciation and to do the extra investment needed to keep up with population growth. And so an extra unit of capital is going to raise steady state consumption. MPK greater than delta plus N. Let's look at the graph here for a minute. If I, actually, that's not very helpful. You go back to the old depreciation, old golden rule picture. So we're missing the graph here, but if the MPK is higher then delta plus n, you've got a bigger slope of the curved thing, which means as you go to the right, the C star thing is getting fatter. C star gap is getting fatter. And that's the case we're talking about. We've got MDK greater than delta plus n. How do we know that? Because delta plus n times k is equal to s times y for it to be a steady state. So the answer is we're below the golden rule level of capital, answer C. Okay, let's talk just a little bit about population growth. There's some interesting alternative perspectives on population growth. There's the Malthusian model predicts population growth will outstrip the Earth's ability to produce food, leading to the impoverishment of humanity. And so basically you get everybody just at the margins of subsistence. In Malthus, it's actually wonderful for the world, but Malthus, in terms of being scientifically right, had the misfortune of writing his theory exactly when it started to, when it was going to be false in the future, or not be relevant in the future. Malthus's model actually described things quite well for the period of time before 1798. But since then, technology's been improving so rapidly that our living standards are higher than ever. But if you go back in time, for most of human history, the Malthusian model is pretty good. That there's kind of a steady state level of population that's determined by if output per worker gets higher than that, then the population grows, and if output per worker gets lower than that, the population shrinks, and that gives you a steady state population. Well, that was true up till 1798, hasn't been true since. Could be true in the future someday, but potentially, but hasn't been true from 1798 to 2020. Okay, Malthus couldn't guess just how much technological progress there would be, and just how that would outstrip these other forces of population growth. The other thing about population growth is it's relative to what Malthus would have thought. It's been remarkable how much population growth has come down. Okay, now there's another way of thinking about population growth, which is that actually not population growth, but the population level contributes to economic growth. Why would that be? More people means there's more geniuses, scientists, and engineers, so faster technological progress. And there's some evidence of this in the very long sweep of history. As world population growth increased, so did the rate of growth in living standards. And historically, regions with larger populations have enjoyed faster growth. Well, let's give some examples. Eurasia, that had the most people, got to the highest technology. Okay, the Americas, North and South America, well, they had the next biggest chunk of people. They got to a pretty high technology level with the Maya and the Aztecs, not quite as high as Eurasia. Australia, until Columbus, that was, America was isolated from Eurasia, and they were both isolated from Australia. Australia had a much lower population and ended up with a lower technological progress and lower technology by the time after Columbus and explorers were traveling the globe, and so the Australian Aborigines were not at high a technological level as the Aztec and the Maya. And then Mike Kramer also talks about Tasmania, which is an island off the coast of Australia, which is politically part of Australia. There was not any serious contact between Tasmania and Australia for a long time, and the Tasmanian technology did very badly. Okay, we're almost done. Let's just summarize things. The Solow growth model shows that in the long run, a country's standard of living depends positively on its saving rate, negatively on its population growth rate. An increase in the saving rate leads to higher output in the long run, faster growth temporarily, but not faster steady state growth. If the economy has more capital than the golden rule level, then reducing saving will increase consumption at all points in time, making all generations better off. But if the economy has less capital than the golden rule level, then increasing saving will increase consumption for future generations, but reduce consumption for people right now. And that's it. Thank you for listening. I want to emphasize that this whole chapter is really just about the capital stock and about that element in economic growth. From my previous lecture, you know that there are many, many other elements that go into economic growth. So, the capital stock is something that's emphasized in the textbook, partly because it's especially easy to think about. So it does matter. It is important. The saving rate does matter, but I don't want you to get an overinflated, a exaggerated picture of how important capital is. The other things are very important too. So, take a peek back at that lecture if you're not remembering this, to see some of the many other things that matter for economic growth. Thanks for listening. Stay safe, and we'll talk. I'll post something again soon.